Good evening. I'd like to welcome you all that have come out on this dark and stormy night to join us this evening. We've waited a few minutes because the folks from embryology are en route but haven't made it, and they have a special reason to be here for reasons that I'll explain at the very end of the program. So we're going to get started with the lecture, and unfortunately they will miss the beginning of it, but I know you've all been waiting patiently. This is an enormously exciting time in astronomy. About 15 years ago, we learned that the universe is much stranger than we had realized. That we learned that we don't understand 95% of the universe. It's made up of something called dark matter and dark energy. And there's really nothing that whets the enthusiasm of a scientist other than a mystery of this nature. So astronomers and astrophysicists today have the luxury of being confronted with a deep and wonderfully challenging mystery to be able to try to solve these problems. Dark energy was a completely unexpected result. Everyone had anticipated that the expansion of the universe, which incidentally had been discovered by Edwin Hubble, Carnegie astronomer, of course, that the expansion of the universe should be slowing down. Just as when you toss a ball up under the force of gravity, it should slow and perhaps eventually turn around and come back. And there was a mystery about whether the universe was certainly slow, and the question the cosmologists had is whether it would rebound or not, or whether it would glide on, expanding forever. Well, in any event, there were two groups that studied this problem, and they each came up with a totally surprising result, namely that the expansion of the universe was accelerating. And I'm proud to say that there was a Nobel Prize that was awarded to the leaders of those two groups, and Mark Phillips, who was a Carnegie astronomer, was a member of one of those groups. We don't understand the nature of this strange phenomenon. It's called dark energy. And energy and matter are equivalent, E equals mc squared. So if one looks at the energy matter inventory of the universe, about 70% of the universe is made up of dark energy. We didn't even know it existed 15 years ago. It's sort of an anti-gravitational force. We've known about the existence of dark matter for a longer time, thanks to the verification of its existence by Carnegie astronomer Vera Rubin and Kent Ford. Vera got the Presidential Medal of Science for this discovery. And we know it exists because of its impact on the motion of stars within galaxies, and that there has to be more mass than we can see to explain the motions of the stars through gravitational attraction. But it doesn't interact with other matter in ways one would expect. It has a gravitational effect, but you don't see other things. So it's you have this fact that another big chunk of the universe is made up of dark matter, matter that is not like the stuff that's around us, made up of protons and neutrons and electrons. And this dark matter accounts for about 25% of the energy matter inventory of the universe. So we have this great dilemma that we understand only 5% of the universe, which is kind of an embarrassing fact for a scientifically advanced period of our time, but of course it's a wonderful challenge and a wonderful mystery, and that's why this is an incredibly exciting time for cosmologists and astronomers. Our speaker tonight, Josh Simon, aims to answer big questions with small objects. Small, of course, being defined in astronomical terms. He uses the nearby universe, that is the region within a few 100 million years, light years, as basically an astrophysical laboratory for trying to understand the nature, in particular, of dark matter, among other things. A major focus of his work has been testing the so-called lambda cold dark matter model, which is a dominant theoretical framework for the evolution of the universe and the formation of galaxies within it. And it embodies our current understanding, which is limited, of course, of the dominance of dark matter and dark energy in the universe. It provides an accurate description of the universe as a whole, but some of its predictions for the properties of galaxies, especially small galaxies, have generally not been borne by observations. And so by making measurements of the motions of stars and gas within galaxies, Dr. Simon has shown that these discrepancies are generally much less severe than previously thought. In the course of carrying out these detailed observations to study dark matter, he became interested in how the galaxies themselves worked. His research now encompasses many aspects of our closest galaxies, including their youngest and oldest stars, their gas and dust, the explosions of stars at the end of their lives, production of chemical elements, and the like. Josh has not been afraid to advance novel ideas. Shortly after he finished his PhD, he attended an invitation-only conference at a German castle, where, ignoring the discouragement of his mentors, he gave a presentation of the possible existence of dark galaxies. That is, entire galaxy-sized objects consisting entirely of dark matter that never form stars. The reaction, I think it's fair to say, at this meeting was skeptical. There was a conference banquet that evening at which an elder statesman was charged with summarizing the conference, and he presented the results of a survey. The attendees were asked the question, which of the following is most likely to exist? The Easter Bunny, the Tooth Fairy, or dark galaxies? The Tooth Fairy got more votes than dark galaxies. In order to mollify Josh, he was awarded a bottle of wine for giving the most provocative talk of the meeting. But the important thing to say is that within a few years, the concept of dark galaxies had gained wide acceptance in the astronomical community, and well-respected senior astronomers have now published papers suggesting that not only do dark galaxies exist, but they found such objects. So Dr. Simon was sort of prefigured a scientific advance in the true Carnegie fashion. He earned his BS degree in physics from Stanford in 1998 and his PhD in astrophysics from UC Berkeley in 2005. After completion of his thesis, Joss was a prestigious Millikan postdoctoral fellow at Caltech. He joined Carnegie as the Vera Rubin Fellow in 2008 and was appointed a staff member in 2010. He is working at the cutting edge of some of the most challenging problems in astronomy, and we're very pleased that he could join us tonight to tell us about his work. So please join me in welcoming Dr. Josh Simon. I didn't say anything that was too long.
Well, thank you, Dick, for that introduction, and thanks to all of you in the audience for braving the rain this evening and coming out to hear about some of the exciting astronomy research that's going on right here at Carnegie. What I'd like to tell you about tonight is galaxies. So my own research focuses on some of the closest galaxies to us, and the idea behind that is that these are the ones that we can observe in the greatest detail and hence understand the best, because they're located, astronomically speaking, right under our noses, just a few 100,000 to a few million light years away. And then we can use what we learn from these nearby objects to make better extrapolations to the vast majority of galaxies in the universe that are located much farther away and that we therefore cannot study in nearly as much detail. What I'll particularly be emphasizing is not just the part of galaxies that we all know about, the stars, but also the hidden side of galaxies, which is made up of a mysterious substance called dark matter that turns out to be far more important to galaxies than the stars are. And one of the key goals of the next generation telescope that Carnegie is leading the development of, the Giant Magellan Telescope, is to provide new clues as to exactly what this dark stuff might be. So I'll begin by giving you an introduction to galaxies. I'm sure that many of you are familiar with what galaxies are, but it's always good to start off on some common ground that we're all comfortable with. And besides, this gives me an excuse to show a bunch of pretty pictures, which of course is half the point of astronomy anyway. Then I'll tell you about the local group of galaxies that our Milky Way is located in, and about some of the other interesting galaxies that are found in the nearby universe. In the second half of the talk, I'll tell you about dark matter, and in particular about one of the theoretical problems in the study of dark matter that astronomers, including me, have been wrestling with for more than a decade now. Okay, so just to make sure that we're all starting off on the same page here, what is a galaxy? Well, as the source of all knowledge, Wikipedia tells us, galaxies are groups of stars and gas that are held together by their own gravity. Galaxies come in an enormous variety of different shapes and sizes. So I think the picture that many of us have in our heads for what a galaxy is something like this beautiful spiral galaxy shown here. And many galaxies are indeed spiral galaxies. There's also an entirely separate class of galaxies called elliptical galaxies. So you can see here, these are just kind of balls of stars. They have no interesting features in them. They have a much less photogenic visual appearance. But astronomers still find these elliptical galaxies interesting, despite their just kind of bland yellowish red color all over, because many of the biggest galaxies in the universe are ellipticals. And we've also determined that the largest black holes in the universe also are generally located in elliptical galaxies. Just to give you a sense of the scale of these images, these galaxies are each, very roughly speaking, 100,000 to a few 100,000 light years across. And that's about the same as the size of our own Milky Way. Not all galaxies are anywhere near this big. There are much smaller galaxies, known as dwarf galaxies, because of their small sizes. And in the dwarf galaxy regime, there are also a variety of different shapes that are found. So there are dwarf elliptical galaxies, which you can see here. These look a lot like the giant elliptical galaxies on the previous slide, except that this galaxy is only about 20,000 light years from one side to the other, instead of nearly 300,000 for the giant elliptical. And the counterparts of spiral galaxies, when galaxies get much smaller, are called dwarf irregular galaxies. When a galaxy is significantly smaller than the Milky Way, it's not able to form and maintain the nice spiral arms that we're used to seeing in images. And you just end up with a system with a pretty irregular kind of structure, hence the name dwarf irregular. Okay, so in terms of shapes, galaxies can be spiral, elliptical, or irregular. And they also span a really enormous range of physical properties. The smallest galaxies weigh only about 1 million times the mass of the sun, whereas the largest can be 10 trillion times more massive than the sun is. The number of stars, or the luminosity of a galaxy, can range from about 1,000 for the very smallest dwarf galaxies that are known, up to as much as 1 trillion stars for the biggest galaxies. And the most compact galaxies that we've found are as little as 100 light years from one side to the other, whereas the biggest ones can be more than 300,000 light years in diameter. Now, what's responsible for this incredible range of different properties that galaxies can have? One thing, obviously, is just size, how much stuff a galaxy managed to accumulate when it was forming. But we've already seen that there are galaxies of similar sizes that look very different, so we know that that can't be the whole story. The other major factor that determines the appearance of a galaxy is whether or not it contains any cold gas. And that's because cold gas is the fuel out of which new stars are formed. So spiral galaxies are rich in cold gas. They're still forming new stars today, and that's responsible for many of the more interesting features in their appearance. On the other hand, elliptical galaxies are filled with hot gas and generally don't have any cold gas left at all. So hot gas, with temperatures of hundreds of thousands to millions of degrees, is not able to form new stars. So elliptical galaxies formed all of their stars billions of years ago, and that's why they look so smooth and boring today. Now, I don't want to go into too much detail here because star formation could easily be its own entire lecture, but just to give you a sense for the impact that the formation of young stars can have on the appearance of a galaxy, here's a picture of the Whirlpool galaxy, M51. Each of these little red knots tracing out the spiral arms in this galaxy are places where a bunch of new stars have recently formed. If you could zoom in on one of these and see it in more detail, it would look something like this, where there's a cluster of a large number of very bright, very hot, very blue, young, massive stars. And those are surrounded by a cocoon of gas and dust that they formed out of. Over periods of tens of millions of years, the fierce winds from these stars blow the gas and dust away. You can see those winds pushing the gas and dust towards the upper right part of the picture around this cluster. And so what you're left with, once the gas and dust dissipate, is just this group of very bright, very blue stars. And so that's why the spiral arms of galaxies have this blue color. Okay, so next let's talk a little bit about what galaxies are made of. One thing, obviously, is stars. That was part of the definition, after all. But it turns out that when you do the accounting, stars only make up about 10% of the mass of a typical galaxy. I just got done telling you that galaxies also have gas in them. The gas is what provides the fuel for forming new stars. It makes pretty colors in the images that we take. But generally, galaxies have a lot more stars than they do gas. They've already converted most of their gas into stars. So a typical galaxy only has about 1%, or at most a few percent, of its mass in stars. We also know that galaxies contain dust. So whenever we see a spiral galaxy oriented edge onto us, like this picture of the Sombrero galaxy, we see a dark lane cutting across the middle of it. This is a thin layer of interstellar dust that's very effectively blocking the light from many of the stars sitting behind it. Even though dust is very efficient at blocking starlight, it takes very little mass of dust to accomplish that. And so dust represents just a tiny fraction of a percent of the mass of a galaxy. Okay, so that's everything that we can see in galaxies, and we're still sitting at just a little bit over 10% of the total mass. So what makes up the rest of the mass? The other 89% of the mass of a galaxy is made of a very strange substance called dark matter. Now, I'll go into more detail later in my talk about dark matter, but for now I'll just say that this is a completely new form of matter that's never been detected before, and it doesn't give off any light, which obviously makes it a bit hard for us to study. Okay, so now that we've dealt with the basics of galaxies, let's move on to some of the specific galaxies that you might be interested in learning a little bit more about. This is a picture of the Milky Way, our galaxy, and even if the only thing that you had to go on was this image, I think it would be obvious that the Milky Way is not an elliptical galaxy, which is just kind of yellowish red in color all over, with the light smoothly distributed and with no gas and dust. Instead, it's a spiral galaxy. Now, in 3 dimensions, a spiral galaxy can be very extended across. It can have a diameter of 100,000 light years or more. But they're very thin. So they're shaped kind of like a DVD, a plate, a frisbee, whatever your favorite round, flat object happens to be. And so you can imagine that if you were sitting on the edge of, let's say, a frisbee and looking up at it, you would only see that frisbee covering a small portion of the sky. And that is why when we look up at the night sky and see the Milky Way, it only covers a small band across the sky. If we lived in an elliptical galaxy, we would see our galaxy filling up most of the sky. If we could move way up above our galaxy by tens or hundreds of thousands of light years, which would be nice, but we haven't figured out a way to do that yet, we think that the Milky Way would look something like this. It has a large bar at the center of it. It has a couple of prominent spiral arms. And the sun is located kind of in between some of the major arms here, about 25,000 light years away from the center. Most galaxies, like the Milky Way, live in small groups of galaxies, with a few big galaxies and a bunch of small dwarf galaxies orbiting around them. Here's an example of one such group. This group has 3 big spiral galaxies in it, and it's named the Leo triplet. Now, for completely unrelated reasons, my younger son is named Leo. Fortunately, he didn't turn out to be triplets. Otherwise, I think my wife probably would have killed me by now. So the Milky Way is located in a very similar group of galaxies. And because astronomers are not very creative at coming up with names for things, this group is called the local group. And the local group consists of the Milky Way, another large spiral galaxy known as Andromeda, or M31, and then a third, somewhat smaller spiral galaxy called M33. And then the rest of the group is filled with about 75 known dwarf galaxies. So here's a better view of the Andromeda galaxy, M31. This is the other main spiral galaxy in the local group. And it's very similar in terms of its overall size and structure to our own Milky Way. It's a little bit bigger. It's not forming quite as many new stars anymore as the Milky Way is. But overall, they're very comparable sorts of galaxies. And it's located about 2.5 million light years away from us. This is the third spiral galaxy in the local group, M33. It's also located about 2.5 million light years away. And it's only about 1/10 as big as the Milky Way and M31 are. Since M33 is oriented in a more face-on way towards us, we can get a much better view of its overall structure than we can for the Milky Way and for Andromeda. And that makes M33 kind of a prototype for many studies of spiral galaxies. And unlike the two bigger galaxies in the local group, M33 does not have any known dwarf galaxies orbiting it. Here's a three-dimensional view of the local group. Milky Way is sitting over here. Andromeda is down and to the right with M33 right next to it. And then clustered tightly around each of these big spirals is a group of these much smaller dwarf galaxies. There's also a few dwarf galaxies just sitting off all by their lonesome in the outer reaches of the group, but most of the dwarfs are concentrated near where the bigger galaxies are. Now let's get a better view of some of these dwarf galaxies. The two biggest dwarf galaxies orbiting the Milky Way are known as the Magellanic Clouds, and they're shown here in a picture from Australia taken at twilight. Now, again, illustrating our lack of creativity, the bigger of the two is the Large Magellanic Cloud. And does anyone want to take a wild guess at what the little one is called? That's the Small Magellanic Cloud. So if any of you have been down to the southern hemisphere, you've probably actually seen these objects up in the sky because they're so bright that they're easily visible with the naked eye. But you might not have realized that that faintly glowing patch of light was actually an entirely separate galaxy located outside the Milky Way. Now, the reason that these galaxies are called the Magellanic Clouds is that the first record of their existence comes from Ferdinand Magellan and his crew as they sailed around the coast of South America in their ill-fated attempt to circumnavigate the globe. Of course, Magellan doesn't really deserve credit for discovering the clouds. The fact that they were up there was obvious to anybody who lived in Africa or South America or Australia for many thousands of years before he came along. But none of those people happened to go back and tell all of Europe about these amazing things that they saw in the sky. Here's a better view of the Large Magellanic Cloud. As you can see, this is a dwarf irregular galaxy. It's almost big enough to be a spiral. And you may be able to just, if you squint, make out some hints of spiral arms coming off the end of this bar structure here. Excuse me. But obviously, this is overall a pretty irregular looking galaxy, and it's located about 150,000 light years away from us. This is the Small Magellanic Cloud. On the left is a picture of the stars in the galaxy. Again, this is a dwarf irregular. It's a little bit smaller than the Large Magellanic Cloud. It's not forming quite as many new stars anymore. And it's located just a bit farther away at 180,000 light years. This picture on the right shows the ionized gas in the galaxy, the gas that's been heated up by the formation of young stars. And I can't resist showing this image whenever I talk about the Small Magellanic Cloud, just because I think it looks so amazing. Every place in the galaxy that these new stars have recently formed has blown a bubble of hot gas around the new stars. And I think you can see the results of that process more clearly in this galaxy than anywhere else in the universe. This is another dwarf irregular galaxy in the local group known as NGC 6822. It's a bit smaller than the Magellanic Clouds. You can still see that it looks pretty irregular. And you can again see some of these bubbles of hot gas created by the young stars. Now, this is a much smaller dwarf galaxy. And this is much more typical of what most dwarf galaxies look like. This is a galaxy known as Leo 2. It's actually one of the more massive of the Milky Way's dwarf galaxies, and it's located about 700,000 light years away from us. Now, if this is what one of the bigger dwarf galaxies around the Milky Way looks like, you can imagine how unimpressive the majority of them are. But astronomers still find these objects fascinating because, as you're about to hear, they turn out to be where most of the action is when you want to learn about dark matter. Okay, so now that we've covered everything that you need to know about galaxies, let's go back to our pie chart, where everything that we can see is just this little slice here. And the other 89% of galaxies is made up of something that we've never encountered before. As you can imagine, this is kind of an uncomfortable situation for us to be in, where the things that we understand make up just a minor component of what's actually out there. And it's a little bit inconvenient for those of us who are trying to make a living by studying the light given off by celestial objects, that most of the universe is made up of something that we can't see. Unfortunately, as most astronomers find out pretty early in their careers, the universe doesn't care that much what we think. But astronomical observations have shown pretty conclusively that this picture of the universe must be basically correct, as I'm about to show you. And so our task now is to try and figure out what this dark matter actually is. Now, one of the first questions that you probably have is, if dark matter doesn't give off any light, then how can we really be sure that it's actually out there? And the answer is that even though the dark matter itself isn't giving off light, we can see the effect that its gravity is having on the parts of the galaxy that do give off light, the stars and the gas. So spiral galaxies are spinning around just like a frisbee. And that means that one side of a galaxy that you're looking at is always moving towards you, the side here. And the other side of the galaxy is always moving away from you. And whenever you have something moving towards you or away from you, the Doppler effect shifts the wavelength of the light that you see. So the light from the side of the galaxy moving towards you is going to be shifted towards slightly shorter wavelengths. It'll be blue shifted. And the light from the side of the galaxy moving away from you is shifted to longer wavelengths. It's red shifted. And that means we can use the Doppler effect to measure how fast a galaxy is rotating. This is exactly the same way that, same reason that an ambulance siren or a train whistle changes pitch as it moves past you. And it's the same way that a radar gun works to measure how fast your car is going, how fast you can throw a baseball, and so on. So we use the speed of the orbits of the stars and gas around the center of a galaxy to tell us what the total mass of a galaxy is. And then that works just the same way as how we use the speed of the Earth orbiting around the sun to tell us what the mass of the sun is. So that gives us a pretty accurate measurement of the total mass of a galaxy. And then we can just take a picture of a galaxy and count up how many stars it contains. We understand stars reasonably well at this point, so it's not too hard to estimate what the total mass of those stars is. What we find when we compare those two numbers is that galaxies weigh about 10 times as much as all the stars in them put together. So it's as if I stepped on the scale one morning, looked down, and it told me that I weighed 1,500 pounds. First thing that I would think is probably that I need a new scale, but after running all the tests that I could think of on my scale, I'd be forced to conclude that there must be something else here that I can't see that's providing most of the mass on the scale. And in the case of galaxies, that something is dark matter. This was discovered in the 1970s, as Dick mentioned, by Vera Rubin, a longtime staff member at Carnegie's Department of Terrestrial Magnetism right here in Washington. So Vera spent most of the decade of the 70s measuring the rotation of spiral galaxies more carefully and more systematically than anyone else was doing. And her measurements of the Andromeda galaxy are shown up here, overlaid on a picture of the galaxy. You can see that this galaxy continues rotating rapidly, even well beyond where most of the stars in the galaxy are located. And after discovering that essentially all spiral galaxies behave in this way, Vera concluded by 1980 that it was inescapable that there must be non-luminous matter, dark matter, located in the outskirts of galaxies. And again, as Dick mentioned, she was awarded the National Medal of Science for this discovery in 1993. Now, the next thing you probably want to know is, what is dark matter? It turns out it's a little bit easier to start out by answering the opposite question: what isn't dark matter? So the first thing that most people think of when they hear the phrase dark matter is that it must be referring to black holes. Dark matter is not made of black holes, and it's also not made of very faint stars like white dwarfs and brown dwarfs. It has no connection to any of the products of stellar evolution. In fact, dark matter is not even made of normal matter, the atoms and molecules that we're all familiar with at all. It must be something fundamentally different. So we think that dark matter is a new kind of subatomic particle, and that's never been seen before. And you can think of this as a little bit like the Higgs boson, which was discovered at the Large Hadron Collider in Switzerland 2 years ago. There was all sorts of stories in the news about that. And the Nobel Prize in Physics was awarded for that discovery last fall. So the properties of the dark matter particle are probably a bit different from those of the Higgs boson, the mass and so on. But conceptually, it's rather similar. Now, the really unique thing about dark matter is that it doesn't interact with normal matter in any way except through gravity. Now, let me give you an example to illustrate what I mean when I say that it doesn't interact. Let's say that I happen to have a neutron and I happen to have a uranium atom. And just for kicks, I decide to throw my neutron at the uranium atom. I have pretty good aim, so I hit it right in the nucleus. And when that happens, the nucleus will split apart. That's how a nuclear reactor works. Now, let's say that instead of a neutron, I had a dark matter particle. And I again tossed it at the nucleus of the uranium atom. But this time, the nucleus just sits there, not noticing that anything hit it. And the dark matter particle just keeps going. It doesn't notice that there was anything there. So dark matter doesn't feel electric or magnetic fields. It doesn't give off any light. The only thing that it can do is pull on other things with its gravity. So the discovery of this new form of matter was initially seen as very strange, as I'm sure you can imagine. But over the past few decades, theoretical astrophysicists have really done a remarkable job of constructing a theoretical framework in which dark matter actually makes some sense. The favored theory that's been developed over that time span is known as the cold dark matter model, where cold just refers to the fact that the dark matter particles are moving through space rather slowly. And this theory does an amazing job at explaining almost everything that we see when we look out at the universe. It explains the cosmic microwave background radiation, the distribution of galaxies through space, the evolution of galaxies through cosmic time, and the overall expansion of the universe. But when we start looking in detail at individual galaxies, then some of the predictions of this theory are not in such good agreement with what we actually observe. And so that's led to the question of whether our theory of dark matter is fundamentally flawed, perhaps our understanding is significantly incomplete, or whether it's simply that observations of galaxies have not been made accurately enough. And much of my research over the last 10 years has been investigating exactly that puzzle. Now, one of the most serious of these problems that the cold dark matter model faces is that it predicts that galaxies like the Milky Way should be surrounded by an enormous swarm of up to 1,000 small dwarf galaxies. And that's illustrated in this computer model of a galaxy shown here. Every one of these bright spots of light should be a dwarf galaxy. On the right is our map of the immediate environment of the Milky Way, and with all the dwarf galaxies that we know about labeled. And I don't think it takes a PhD in astronomy to tell that there's a bit of a disagreement here. So our theory is telling us that there should be up to 1,000 dwarf galaxies orbiting around our Milky Way. And as of 2004, after decades of going out and looking for these dwarf galaxies, we'd managed to find a total of 11. So not only are we missing 80% of the mass of the universe, now we can't find 99% of the galaxies either. So that seems like a big problem. Fortunately, over the last decade, we've actually made significant progress in discovering new dwarf galaxies, as I'm about to show you. And in order to do that, I need to back up a little bit and tell you how astronomers go about trying to find dwarf galaxies. In the past, dwarf galaxies were found using photographic plates, images of the sky taken on glass plates with essentially a coating of film on them. There was a survey called the Palomar Sky Survey that took images, thousands of them, covering the entire sky over the course of a few decades starting in the 1950s. And then if you wanted to find dwarf galaxies, astronomers would sit down with a stack of these plates and a magnifying glass and pore over them inch by inch until they saw something that they thought looked like it might be a dwarf galaxy. So while discovering a new galaxy sounds like something very glamorous, in fact, it involved an incredible amount of just very tedious, mind-numbing work. And just to add insult to injury, the galaxies that you found that way were pretty obvious. So here's an example of one of the dwarf galaxies found by visual examination of plates in the Palomar Sky Survey. You can clearly see a faint group of stars at the center of this image. That's a dwarf galaxy. Here's an adjacent piece of the sky with nothing there, and your eye can easily see that. So it's not that these dwarf galaxies were actually that hard to find, it's just that the sky is a really big place, and so it helps a lot if you know where to look ahead of time. Recently, a new sky survey has been completed, and this is known as the Sloan Digital Sky Survey, and it makes a couple of really important advances over the earlier Palomar Sky Survey. First of all, the Sloan survey uses modern digital detectors, the same things that are in your digital cameras. So that digital detectors are about 100 times more sensitive to light than film is, which means we can see much fainter stars, and therefore we can potentially detect much fainter dwarf galaxies. And the even better thing is that since the data are stored in digital form rather than with photographic plates, I can search for dwarf galaxies without risking either my sanity or my eyesight. So I can just go online, I can download a list of every star that the Sloan survey has observed. And then I can write a computer program to search through that list of stars and identify groupings of faint stars that look like they might be dwarf galaxies. As an example of how that works, here again are pictures of two adjacent pieces of the sky. One of them has a dwarf galaxy in it, and one of them doesn't. Since these dwarf galaxies are much fainter than the ones found by the Palomar survey, you can't tell me just by looking at these pictures which one has the dwarf galaxy in it. But if I show you the density of faint stars determined by my computer program, then it becomes immediately obvious that there's a bright spot indicating a large enhancement in the number of faint stars at the center of this image, and there's nothing at all over here. So this gives us a way to find galaxies that are too faint to see in images. So let's consider where things stand at the moment now that the Sloan survey has been completed. Prior to the Sloan survey, as of about 10 years ago, we had found 11 dwarf galaxies orbiting the Milky Way. Sloan has now discovered 15 new ones in just a few years, more than doubling the entire combined efforts of the astronomical community over all of recorded history previous to that. So the obvious answer to how many dwarf galaxies we have now would be 11 plus 15. But it turns out that Sloan didn't observe the entire sky. It only observed about a third of the sky. So we actually need to take our 15 new dwarfs, multiply them by a factor of 3 to account for what we expect to be out there when the rest of the sky has been looked at more carefully. And that gives us 45 of these new ultra-faint dwarf galaxies, plus our 11 old dwarfs. That gives us 56 dwarf galaxies orbiting the Milky Way, a factor of 5 more than we knew about just 10 years ago. That seems like a major improvement, but remember that our theory predicts that there should be 1,000 of them out there, so we're still missing more than 900. And take note that these data are being plotted on a logarithmic scale here. So even though these things look like they're starting to catch up to our prediction, in fact, we're still dramatically short of all the dwarf galaxies that we expect to find. So now we have to wonder whether there could be an even larger population of yet fainter dwarf galaxies that don't even show up in the Sloan survey. The only way to answer that question is going to be with a new telescope that is starting construction later this year in Chile, just down the road from the Giant Magellan Telescope. And this is called the Large Synoptic Survey Telescope, LSST. What's unique about LSST is that it's going to have the biggest camera that's ever been built. So you can go out and buy a digital camera now with 30 megapixels, maybe even a bit more. The LSST camera is going to have 3,200 megapixels. And this huge camera is going to enable it to take images of the entire sky every 3 nights. So whereas before it took the Palomar survey a decade or so to cover the whole sky, LSST can do that 3 nights, and it's going to keep doing it every 3 nights for a period of 10 years. So that's going to enable us to do a couple of really new things in astronomy. First of all, you can make a movie of any piece of the sky that you happen to be interested in and see how things move and change on a time scale of just a few nights. And that will open up a new parameter space for discovery in astronomy. The thing that I'm more interested in is that LSST will take hundreds of images of every piece of the sky, and you could just add all those images together and create what's effectively the most sensitive image of the sky that can ever be obtained by a telescope that's not in space. And that will be a really amazing tool for finding the faintest possible dwarf galaxies. Now, the problem that we're going to face once LSST is up and running is that it's almost certainly going to find hundreds, maybe even thousands, of these groups of very faint stars that might or might not be dwarf galaxies. Now, back when we were studying dwarf galaxies that looked like this, that you could clearly see by eye, it wasn't that hard for astronomers to agree on what actually was a dwarf galaxy and what wasn't. Now that we're in the position of studying dwarf galaxies that look like this, there really is a dwarf galaxy in this picture, even if you can't see it. It's going to be much more challenging to determine whether these groups of stars found by LSST are actually galaxies or not. Now, to see how we're going to determine whether they're dwarf galaxies or something else, let's go back to our original definition of a galaxy. Now, up until recently, this was a perfectly fine layman's definition of what a galaxy is. But over the past few years, it's become apparent that we actually need to add a new criterion here. And that is that the mass of the galaxy needs to be provided mostly by dark matter. So we have a group of stars and gas that's held together primarily by dark matter. Every galaxy that we know of has significant amounts of dark matter in it. Every group of stars that we've ever seen that isn't a galaxy has no evidence for containing any dark matter. So it's really the dark matter that is the crucial distinction between galaxies and other kinds of objects. So in order to determine whether there's dark matter in these candidate dwarf galaxies found by LSST, what we have to do is measure how fast the stars in them are moving around. So the more an object weighs, the more gravity it has, and the more gravity something has, the faster it makes things in its vicinity move. To take a slightly more everyday example, if you were standing on the moon and you jumped up into the air, the moon is a relatively small planetary body, so it doesn't have very much gravity. It would pull you back down relatively slowly. So that means that you can jump higher on the moon than you can on the Earth. In contrast, if you were standing on Jupiter, ignoring for the fact that Jupiter doesn't have a surface to stand on, and you tried to jump, then Jupiter is the most massive planet. It has a very strong gravitational field, and it would pull you back down quite rapidly. So we can use the motions, the speeds at which things within an object are moving to tell how much it weighs. Now, the problem is with these candidate dwarf galaxies that the stars in them are incredibly faint, as you've seen in the last few pictures that I've shown you. And so the only way that we're going to be able to measure the speeds at which they're moving accurately enough is with the biggest telescopes that we can currently conceive of, like the Giant Magellan Telescope. So here's an example of what we expect to see with the GMT, depending on whether these candidate dwarf galaxies that LSST is going to reveal are really dwarfs or are just clusters of stars without any dark matter in them, or just random groupings of stars that happen to look like they're all located in the same place, even though they actually aren't. So if what we're looking at is just a group of stars without any dark matter in it, then the stars in it will be moving around very slowly, just half a kilometer every second, or only about 1,100 miles an hour in more human terms. On the other hand, if we're looking at things that are dwarf galaxies, they'll be much more massive because most of the mass is provided by the dark matter, and the stars will be moving much more rapidly, therefore, about 10 times faster, 5 kilometers per second, or 11,000 miles an hour. So by using GMT to measure how fast the stars are moving in all of these objects, we'll determine how many dwarf galaxies there are orbiting the Milky Way, and whether this problem that we have of all of the missing dwarf galaxies can finally be solved. But there's a possibility that even after all that work, we might still find that there are far fewer dwarf galaxies than our theory predicts. And at that point, we'd have to face what's potentially a nightmare scenario for astronomers. What if most of those 1,000 dwarf galaxies that are supposed to be out there never formed any stars? What if they're just silently orbiting around the Milky Way as naked clumps of dark matter, known as dark galaxies? So that seems like it would be a pretty insurmountable problem. If most of the predicted dwarf galaxies are just made of pure dark matter, they don't have any stars in them, then what hope do we have of determining whether they're actually out there, as our theory predicts, or if they're not there and the theory is wrong? Well, it turns out that particle physicists have recently come up with a potential solution to this problem. So you're probably familiar with the idea that if you have matter and antimatter and you bring them together, they annihilate each other and produce a burst of radiation. So for example, this proton and this antiproton, if they hit each other, will turn into radiation in the form of gamma rays. Gamma rays are photons, just like normal light that we see, and like X-rays, but they have much higher energies. So these gamma rays can be 1,000 or 1,000,000 times as energetic, even as X-rays. And it turns out that dark matter can do the same thing. And you don't even need to invent anti-dark matter to accomplish that, because a dark matter particle and a dark matter antiparticle are actually the same thing. So all that has to happen is that any two dark matter particles hit each other, and they annihilate each other and produce gamma rays. And unlike dark matter particles, gamma rays are something that astronomers know how to detect. In particular, a few years ago, NASA launched a new space telescope called the Fermi Space Telescope, which is by far the best gamma ray telescope that's ever been built. And it might just be sensitive enough to detect some of these gamma rays coming from dark matter particles running into each other and annihilating. So this is an image of what the sky looks like with the Fermi telescope. This bright band across the middle of the map is the emission from our Milky Way. And that glows in gamma rays just like it does at every other wavelength. And then most of the gamma rays coming from below and above the Milky Way are from other galaxies. Over the past few years, there's been a growing body of evidence and excitement that there are more gamma rays coming from the center of our galaxy, right here, than can be accounted for by the things that we know of there. And there was a lot of news coverage earlier this month on the possibility that this excess of gamma rays at the galactic center might be coming from these annihilating dark matter particles. Now, the problem with looking for dark matter at the galactic center is that it's an incredibly complicated place with all sorts of things going on that are producing gamma rays. So for example, the center of our galaxy has a supermassive black hole in it that weighs 4 million times as much as the sun. And supermassive black holes give off a lot of gamma rays. The center of our galaxy also is experiencing vigorous star formation. It's forming lots of young massive stars. Young massive stars explode as supernovas, and supernovas produce lots of gamma rays. Since it's been forming new stars for hundreds of millions, if not billions of years, there are also many old supernovas there, which have left behind small black holes and neutron stars known as pulsars. And, stop me if you're getting the picture here, small black holes and pulsars produce lots of gamma rays. So even though there seems to be an excess of gamma rays coming from the galactic center, if we're even slightly off in our estimation of how many gamma rays should be coming from the big black hole, the supernova explosions, the pulsars, then that could account for this apparent excess. So the only way that we're actually going to be able to convincingly determine whether we're seeing dark matter annihilation here is by seeing the same sort of signal from someplace less complicated. And that's where the dwarf galaxies come in. So to a gamma ray astronomer, dwarf galaxies are pretty much the most boring places in the universe. There's absolutely nothing going on in them that should be producing any gamma rays. And so you can be pretty confident that if you see any gamma rays at all coming from a dwarf galaxy, they must be from the dark matter. And so over the coming decade or so, we're going to be looking very carefully at, first of all, the dwarf galaxies that we know of, the new dwarf galaxies that we're expecting to find with the next generation of telescopes that we're building, and finally the rest of the sky where there could potentially be dark galaxies lurking, which don't have any stars in them, but which might still be glowing faintly in gamma rays. And if we see gamma ray signals coming from any of those objects, then that would be very strong evidence that, that our understanding of dark matter is correct, and that will enable us to get a total count of the number of dwarf galaxies that are orbiting the Milky Way. And hence we'll be able to conclusively test this prediction of our best theory that there should be many more dwarf galaxies than we actually observe. Okay, so that's what I wanted to tell you about this evening. Let me just take a few minutes to recap some of the highlights that I hope you'll remember. So first of all, we talked about galaxies and how they're made primarily of dark matter, with the stars and gas and the dust making up just a small fraction of the total mass of a galaxy. So you can think of a galaxy as a little ball of stars surrounded by a much larger cloud of dark matter. Dark matter is a new kind of subatomic particle that is detected via its gravitational effect on the stars and gas in galaxies. And we now think that we have a pretty good theory of dark matter that explains many things very well, as long as we don't look too carefully at individual galaxies, in which case we run into problems like the fact that it tells us that there should be at least 10 times as many dwarf galaxies as we've actually been able to find. But we've recently been making very good progress at discovering new dwarf galaxies, and so the prospects now look pretty promising over the coming decade, perhaps a little longer, to obtain a comprehensive census of the number of dwarf galaxies orbiting the Milky Way, by combining data from telescopes like the Fermi Space Telescope, the Giant Magellan Telescope, and LSST. And that will provide us with a comprehensive test of this prediction of our theory that there should be thousands of dwarf galaxies out there. And that will tell us whether we've managed to successfully understand dark matter despite not being able to see it, or if our theory is wrong, or at least incomplete, and perhaps dark matter will turn out to be even stranger than we might have imagined. Thank you. Okay.
Well, we've had a wonderful survey of dark matter, and we have some time for some questions. There are microphones on the aisles, and I welcome those who'd like to follow up with Josh to come to the microphone and ask questions we'd like to. Let me just get started with one, that you did talk about the excess of gamma ray emissions from the galactic center.
Sure.
But when you described where you thought dark matter should be, it was supposed to be at the periphery of galaxies to hold everything together, and that seems inconsistent.
So dark matter is concentrated at the centers of galaxies. There's more of it there than in the outskirts. The reason that it's easier to detect the effects in the outskirts is that there aren't as many stars there. So in the center of galaxies, we can measure how much mass is there, but most of the mass is actually provided by stars, even though that's where the dark matter is concentrated. In the outer parts of galaxies, there are very few stars, and so most of the mass is provided by dark matter. And so that's where its effects are most apparent, even though there's more of the dark matter in the centers of galaxies. That's actually a completely separate problem in the study of dark matter that I didn't get into tonight, but which there's also been a lot of recent research on.
Well, let me invite anybody who has a follow-up question to ask. And please. The acoustics are poor here, so let me invite you to come to the microphone. Please.
Hi. Hello? Okay. You said that we could only detect dark matter and measure it by its gravitational effect. Then you said we know that two dark matter particles will give off gamma rays when they interact. Could you go into some detail about how we know that?
So we don't know that. That's a theoretical prediction. In many of the models of dark matter that theoretical physicists and theoretical astrophysicists have come up with, that will be the case. But there are other kinds of dark matter particles that could potentially exist where they would not be able to annihilate each other and turn into gamma rays. But that's something that the currently favored models predict should be the case. And so it's something that we're very excited about trying to do, because it gives us an unforeseen way of potentially actually being able to detect dark matter, which we didn't know about until recently.
Thank you.
Please.
Hi, Josh.
Hi, Mike.
So why are these dwarf galaxies so faint? Why don't they have a normal distribution of stars like regular galaxies do?
Well, we don't really know the answer to that yet. So as I mentioned early on, galaxies have a wide variety of different sizes. Some of them manage to accumulate more stuff than others. And that primarily depends on how much gas they obtained at early times back when galaxies were beginning to form 12 or 13 billion years ago. And it can also depend on how quickly they were able to build up their dark matter. So the ones that assembled a lot of dark matter early on then would have been able to get a lot of gas. The ones that have the same mass today, but their dark matter assembled more slowly, they could have had their star formation suppressed by the ultraviolet radiation coming from all of the other galaxies, which heats up the gas in them. So then it's not cold gas, it's warm or hot gas. And as I mentioned, warm or hot gas in galaxies is not able to form stars. But there are many different theories out there trying to explain why there are dwarf galaxies that apparently have the same mass that span a factor of 10,000 in the amount of light that they give off, the number of stars they contain. And so that's something that both theoretical astrophysicists and observers like me are still trying to figure out.
Okay, our last question.
Thank you for the fascinating talk. There is some theoretical physics speculations out there, or models, that the origin of dark matter is connected to zero-point energy and fluctuations of the quantum vacuum. What are your thoughts about that?
I don't think we have any idea yet whether or not that's the case. There are certainly models out there in which dark matter and dark energy are related somehow, but since we have even less understanding of dark energy than we do of dark matter, I think it's really premature to conclude anything one way or the other.
Well, we've had a fascinating tour this evening of one of the great challenges in astronomy of trying to understand dark matter. And I really appreciate that you've having shown us both beautiful images and team. These are awards that we created a few years ago to recognize at Carnegie. They recognize the fact that we are all, the scientists here, and Alison Pinder of the Department of Embryology, come up on this stage. Our first award goes to Alison Pinder of the Department of Embryology. Alison has managed the biopolymer core facility for over 20 years, an operation of fundamental importance to the research endeavors of the department. There have been amazing discoveries in biology over the past 20 years, and really a prime factor in progress has been the tremendous advances that have occurred in equipment and instrumentation. Allison has been a singularly important staff member because of her capacity to stay current with an increasingly larger data sets that these pieces of equipment provide, and their increasing sophistication. She's not only kept up, she's excelled at every step in dealing with them. Let me give you an example. There recently has been the advent of so-called deep or next-generation sequencing machinery. Allison was able to master a very complex instrument and develop skills to meet the increasingly specialized and exacting needs of individual research projects. During its first years, the machine had significant bugs. Allison dealt very effectively with mechanical flaws and difficult data issues. Largely because of her efforts, the productivity of the users of this machine at embryology significantly surpassed that of most other institutions that had acquired the same powerful technology. The machine became and continues to be an indispensable workhorse. Because of her broad biological interests, basic knowledge and expertise in diverse animal models, Allison readily comprehends the projects and needs of our investigators. She has tackled many problems and surmounted what others might consider experimental roadblocks. One of her greatest assets is her flexibility. In the words of her nominator, Allison Pinder is a powerful force behind the successful science at the embryology department. I'm pleased to award you, Allison, with this certificate and this medal to symbolize your service to science here at Carnegie. And let me say that a check will catch up with these. I know you're interested in that. And I want to really thank you for all you have done for Carnegie and for our scientists. So thank you very much.
Thank you. Thanks so much.
Our next medalist is Mary Horan of the Department of Terrestrial Magnetism. Mary, could you come up? Mary has been the geochemistry laboratory manager for over 17 years. Her job involves technique development, the training and supervision of postdoc students and visitors, keeping the laboratory ready for the research activities of our geo and cosmochemistry scientific staff. She's become a pivotal contributor to TTM science. Often visitors feel so indebted to her selfless support of their work that they involve her as a co-author on the manuscripts that result from their visits. Recently, Mary diagnosed the existence of excessive airflow in the laboratory fume hoods in the face of contrary evaluations by several HVAC contractors. Mary obtained the equipment necessary to make the airflow measurements herself and then assembled the data with such clarity that the problem could not be evaded or overlooked. An HVAC contractor who specializes in laboratories confirmed her measurements and evaluation of the problem, and we finally got it fixed. Mary's supervision of the resulting renovation assured that necessary work was completed on time, on budget, and in exactly the manner required. Mary also has her own research activities. She has 46 publications, 12 of which are first authored, an H index of 22, and an average citation per page of 35. We know of no other lab manager anywhere in the world with a comparable high-level research career. What sets Mary truly apart is the professionalism and pride she takes in the progress and success of all the users of the chemistry lab. She's happy to see people use the facility, get data, write papers, and produce the high-class science for which Carnegie is famous. I'm pleased to award you with a certificate and medal in honor of your contributions. And let me say, there's also a check for you. Well, we're deeply indebted to Allison and Mary and to the many other Carnegie support staff who sustain the institution. And I'm very pleased that we have the opportunity to recognize them every year for the great work that they do. I'd like to invite you all to join us in a reception in the adjacent room, and we're now adjourned for the evening here. So thank you.